Hi, so we're here to show our project's code base, just very briefly go over it, and then show what running the code actually looks like. So let me move us onto a screen share now. All right, cool. So this is the main code base, and it's deceptively complicated because it's only several hundred lines of code, which doesn't seem that much, but it does tie into a lot of different components, all the way from, gems and framework and RLlib to Flow and Sumo itself. It's a lot of different moving parts that are working together. Now, fortunately, if you're wanting to look at, try this stuff out yourself, you don't have to. We already have some pre-existing scripts, like here's the RLlib script, and you don't have to worry about it. Um, we've got that handled for you. Um, so I'm going to first demonstrate what the baseline GUI then looks like, then pi saturation with no delay and with added delay, and then the RL lib stuff. And I will in their evaluation stage, and I will also show how you would train something in RLlib, a controller in RLlib. So here's the first one. Oh, yeah. There we go. Oh, okay. So first of all, I'm going to show how you would get into the correct operating environment. So first thing I'm going to do is I'll show you that I did git pull flow and placed it. If I can find it, I'll just rep for it. So I put it right here. And we have our project's code right here as well. So the first thing I'm going to do is run the baseline where all the cars just drive in a human style. But first, we got to get into the shell. So for us, what it is load desktop latest.sif as according to the instructions we talked about. Then the next thing you need to do is update the Python path if you haven't already, so that it accommodates the new flow repo and your project code. Well, our project code. Oh, there we go. And then everything else that already existed. Once we do that, then we can just go right into the flow project. And then we would do Python 3 for us test baseline dot py. Actually, hang on, I'll do it with the arguments. So we'll say we only want one rollout, and we will say our render mode should be Zumo GUI. Oh, I missed an underscore again. I'm missing underscores a lot right now. And this is probably something you could just reference back in the paper. Um, for this, for the baseline stuff, we have to manually annotate the red card, which would normally be running a standard controller, but in this case, it's just running the human controller like all the other cars. But the manual annotation we were doing causes like these annoying flashes. So yeah. And then you can see the stats for that particular setup. And if you had multiple rollouts, you would have the array printed out right here. And then you can just type in none if you just want to, and then have as many rollouts as you want to calculate the statistics. Because go down here, we have it highly parallelized right here. In order to, since each rollout and interaction with Zumo causes all these child processes to be spawned out, we use the multiprocessing backend to keep things uncomplicated. And for us, since on this machine we have 12 processors, we say there's 10 rollouts that can be running at a time. All right, so now, yeah, now I believe it's time to yeah, it's now time to talk about delay. Yeah, it is time to talk about delay. I mean, doing high saturation first with no delay and then with delay. So we're gonna do num rollouts. One render mode. Zumo GUI, and then we're gonna first start with a delay of nothing. Just to show you how it normally behaves. Long story short, it helps with the stop and go waves, but the stop and go waves will still eventually appear. For the record, we were just using the default parameters that have been derived for this by saturation controller from the previous research that our lab has done. So it's totally possible that there might be some other parameters that would help and completely dissipate it. But we chose to keep the parameters exactly the same as before. Now, this is what happens when you have a delay of 5. Yep, and it does the shooting. Pew! Oh, that's not good. So, yeah. Now that that's about to be done, I now have to talk about the RL controllers. So I'll first show how you evaluate it once you've trained it. Which is it's relatively chill. All you got to do is pick the so for us, the one with no delay is the one the controllers that are trained with no delay are stabilizing the ring. And for us, it's gonna be this one. Rollouts. Oh, hang on, I need to say checkpoint 2500. Num rollouts 1. Render mode, Sumo GUI. And then yeah. Hopefully I didn't mistype anything, or that would be pretty awkward. So again, also another thing to remind you, the first GUI for some reason just always exits. We don't know why this happens, but we're able to just keep going anyway, so we don't really mind it. So one thing to keep in mind is that we're loading the environment that the controller, reloading the environment parameters that the controller was trained on, which come with the delay parameter already built in. So that's why we didn't have to specify it in the command invocation, because it already knows that it has a delay of 0 seconds. So you can see here, you just see pretty standard behavior as you would expect. Now, I know this is a little confusing. We have 1, 2, 3, 4, but then the fifth one is just delay. It should probably just say 5. When we submit this to you, it'll probably, because we're going to give you guys the model parameters that we've trained as well, and those will probably just say 5 on them. It'll just say 5 there. And where you see the other one, it will say delay 0. That way it'll be pretty easy for you guys to keep track. Yeah, so anyway, for us, we're picking that run because we ran it twice. So anyway, let's run it now. Now, after the 75-second burn-in happens, we'll see the gap start to slowly widen. But otherwise, The RL controllers at every level of delay are still fairly safe. Their percentage on the safety monitor is almost always 100%. Versus the pi saturation controller, which is not. But yeah, otherwise, your controllers do tend to perform quite a bit better than the pi saturation controllers at these high latencies. So now I need to talk about also the stats here. So this is when you're running on RL, this is your reward, the cumulative reward during that rollout. This is the average velocity of the cars. This is the standard deviation of the cars. And this is the percentage of the times from 0 to 1 that the safety monitor marks the situation as safe. So 100% or 1 is good. 0% is really bad. And actually, hang on, if we can go back to the pi saturation. Yeah, I might not be. Oh, here we go. So as you can see here, it goes down to about 85% for the safety monitor. So now that we've shown all that stuff, I'm just going to quickly walk through all the code here. So the safety monitor right here just marks some situations that we don't think are safe. And if that happens, it returns false, which becomes a 0. And then otherwise it's a 1. So anyway, if it's above 6 meters a second, so the theoretical optimum velocity of the cars never exceeds 6 meters a second with these rings that we have. So anything above 6 is obviously bad. If our time headway is less than 2 seconds, or if our TTC is less than 2, we mark these as unsafe. Otherwise, yeah. So that's that monitor. We also stored, this is the first run of statistics that were not with the monitor. This is the second run of statistics where the monitor is present. Now, this is the pi saturation controller. This is just used verbatim from the flow code itself, except that we now have an artificial delay that is invoked within here. And we have this stuff commented out so that it plays nice with getting our state from the environment itself. Because beforehand, it would just get its state directly it would just derive its own state directly from like ground truth. Then for the RL lib stuff, actually, no, we'll first talk about what baseline looks like. This is the baseline configuration, as you can see here, where it just has the delay incorporated directly in, like so. And this is just for the configuration when we are running it on the baseline instead. This is for the pi saturation controller. So all we have to do, we add the human controllers, and then we add our own controller, which has its own acceleration controllers. Now, something that we need to talk about are the different parameters. Here are the discrete simulator steps in seconds, which is for us 100 milliseconds. And then we have the name, how it's saved into the TensorBoard log, which is for us in array results. The environment class that we're using, which we'll get to that in a second. Then once we get down into the environment, we have 75 seconds of warm up or burn in. Our time horizon is 300 seconds on top of that, or 5 minutes. Now we do maximum acceleration, deceleration is easy, but here's the weird thing. So the ring length, when it's initialized in the simulator, is randomly generated between 220 meters and 270 meters. So this is the maximum maximum potential length we get. This is our minimal length. The observation delay is what is passed in from the command line arguments, and it's directly created like so. And then we just have some additional network parameters, as you can see here. which these are actually just kept verbatim from the original ring simulations that we had in the framework. We wanted to change as little as possible, because obviously the more things we change, the much harder it is to attribute the change that the changes that happen in our simulations to the delay that we've invoked. So we did try to keep our changes to the simulation framework relatively straightforward. I mean, we had to make some non-trivial changes, but I don't think it was anything particularly bad. Now we do need to talk about the environment. So this is actually directly derived from the wave attenuation environment that is implemented in the simulator. We overrode what we needed to in order for the communication latency to be invoked. So we have the ground truth state, which is follows more or less what was expected from the parent class. However, we have it so that, except for the very first observation, the update only happens once we gone past the delay length since the last update, which can be all the way up to 5 seconds. In which case, then we update it like so. And then we also have a patch through function for using the safety monitor. And now, so as you can see here, we just run the simulation loop. This is our loop for the baseline stuff here. These 3 files are basically the same across each one. I mean, I think there's some subtle differences, if I remember right, especially with the RL loop one, because you have to run inference at the same time. So if you go here to our loop, we are computing the action for the agent, and then we're stepping. Now, a weird quirk of the flow architecture is that, so when we do the compute action, it's just referring to the brain reboot. It's just referring to basically some RL lib code. So if you go back to up here, because it's where it says RL, there's an RL controller. I guess we don't have to directly import it here, but we do have to import it. Oh yeah, it's just here. So if you look at the implementation for the RL controller within the Flow framework, it's just empty. Because instead what happens is that if you go to the parameters for the RL controller, the parameter, when you initially train, the parameters are just set up here. And then it Flow has some code that will then create the agent for you. Which, I mean, it's convenient. But like, oh, I mean, I misspoke. It's RL lib itself. And so I just pass in this stuff which says we want it to be PPO, and then we describe the size of the hidden layers. Otherwise, you just stick to the defaults. So if you went here to the default configuration, it has an entire suite of parameters that are in there. Where the activation function is Silu. I'm used to the activation function for these neural networks being Relu, but in our case, it's Silu. So, and then there's no activation function at the end, obviously. We did have to pick a lower learning rate. They wanted us to be, the default parameters were saying, especially in the flow itself, we're saying 5 multiplied by 10 to the -5. We had to do -7. But otherwise, we kept the parameters the same as in the flow RL lib tutorial. Anyway, once that then gets spawned and you've created that, then once you're actually in the simulation loop, you can just compute the action at each time step and do that. Anyway, this now gets back to the final weird thing. With the RL controllers are not handled in the same way any of the other controllers are. Like the pi saturation controller and the IDM controller, uh, they're just invoked by default in the base environment class, along with their prescribed actions, without you having to do this. And so the way Flow expects you to do it is that you compute for any of your like RL based vehicles or AI driven vehicles or whatever you want to call it, outside of the basic simulation step, you will compute the action and then you'll feed that into the environment itself, which I guess was made so that, you could use whatever um, reinforcement learning or, deep learning framework you wanted. Uh, but it is definitely a little, um, it does feel a little, stilted a little bit, but it does give you some extra flexibility. Um, yeah, okay, I think that about covers everything. Also, last but not least, we did have a Slurm script because we did train all of these on a supercomputer because it was just faster than running it on a laptop. Because on one node we could have like 40 CPU cores versus on a laptop we have 12 slower cores. So yeah, all right. Thank you so much for listening.